Lab 4, Spring Oscillation by Colin Funkhauser. The purpose of this lab is to investigate oscillating motion of a free-moving weighted spring in x and y direction and compare it to a computational model. We can plot the x direction and the y direction of the observed and computed spring's motion, as well as the change in energies of a computational model. The results show that the change in total energy is zero throughout, and the predicted model fits the observed model relatively closely. So the physics concepts are Newton's second law, which state that force is equal to the change in momentum over the change in time. In deriving this, we can find that the velocity is equal to the initial velocity plus force over mass times time. Deriving this, we can find the position update formula, which states that a final position is equal to initial position plus velocity times change in time. Continuing, we use the energy principle, which states that energy is neither created or destroyed and is equal to the work of the surroundings plus any thermal energy. A total change in energy of a system is equal to a change in energies of its parts, such as kinetic energy, potential gravitational energy, and potential spring energy in this lab. So the system of this lab is the hanging weight, the earth, and the spring mounted to a fixed point, and we are assuming that there are no other surroundings inputting any energy into this system. Since no surroundings are adding energy to the system, the total change of energy within the system is zero. The initial conditions, the mass of the ball was 0.402 kilograms. The weight's position was negative 0.116 meters in the x and negative 0.665 meters in the y. The weight had no initial velocity as an assumption, and gravity is 9.8 meters per second squared. The spring constant was 6.83 newtons per meter, and the relaxed length is 0.123 meters. The code to model the movement of the spring shows the calculation of the force of gravity as well as the force of the spring, and combining those gives us the net force. We can update the ball or the weight's velocity with the update velocity formula and update the position of the weight with the update position formula. We can also update the length of the spring using the spring, its relaxed length, and the update position formula. Calculating the energies, we use the kinetic energy formula, 1/2 mass times velocity squared. And for the potential energy, we use mass times gravity times height. And for the potential of the spring, we do 1/2 spring constant times length squared. And combining all of this, we get the total energy, and combining the change in those energies gives us the delta E, or the change in energy. Looking at the graphs, where the blue is the model and the red is the experimental, we can see that the model closely tracks the experimental x position and y position with slight variations due to user error and other sources of error that will be discussed later. The energy graphs of the computed spring show oscillating potential energies and kinetic energies following the movement of the weight, but the change in energy remains constant throughout the entire experiment at zero. The initial velocity of the modeled spring movement could have deviated from zero, which would affect the initial conditions and bring rise to error in the modeled graph and the observed graph, and as well as the computational model does not take into account air resistance or other form of frictions, which will affect the closeness of the computational model and the observed graphs. Is the energy principle justified for the modeled system? In this lab, the energy principle is justified because the potential energy of the spring is opposite to the potential energy of gravity, and adding to the kinetic energy equates to zero overall. The change in energy plot shows a net zero change in energy between the potential energies and the kinetic energy, which aligns with the energy principle. Looking at the period of oscillation between the x-axis and the y-axis, the period of oscillation for the x-axis is about 1.8 seconds, while the period of oscillation for the y-axis is 1.6 seconds. These oscillation periods are relatively close but not exact because of drag. They should not be different periods, though, because the spring coefficient should be constant. To conclude, the computational model closely models an observed motion of the oscillation of springs with slight error due to variable start conditions and real-world friction. The computational model being close does allow us to confirm the energy principle being the sum of all energies of the system, which is zero.